Hey guys, today we're going to talk about proof by cases. Not everything is going to move quite so straightforward as it did last time. Sometimes our problem is going to act very differently depending on our situation or like the type of variable that we're plugging in. And for these problems, you need to break your statement into cases so that you can exhaust all the possibilities. Very common cases. Maybe if you want to talk about something happening in the integers, you would want to break it up into even and odd numbers. Another possibility is we want to talk about positive, negative, or zero. This goes very well with R. Another one is breaking it up into things that are 1 or bigger or smaller than 1. Why in the heck would we want to do that? Consider x squared. If you plug in 3, it's going to get bigger because that's going to be 9. If you plug in 1/3, that's 1/9. So now it's gotten smaller. And so it's a very different behavior depending on what kind of numbers we're plugging in. This is not an exhaustive list. This is just kind of like the first 3 that came to mind for me when I was trying to think of what might be helpful to get this rolling. Let's start with an example. We've got 3x squared plus x plus 14, and I want to prove that this is going to be an even number so long as I'm plugging in an integer. So like immediately I'm sitting here going, well, what do I do with it? I can't divide it by 2. What do I know about x? I just know it's an integer. I need more information is what I feel like. So let's break it up into cases so that we can have more information. So case 1, we're going to do even and odd, just like the example that's highlighted. Why? Because an integer is either an even number or it's an odd number. And that's going to give us something to plug in for x. And I know how to do English. X is even. There we go. So if x is even, we can start off with assume x is even. Then there exists an integer k such that x is equal to 2 times k. Now I'm using a little bit different vocabulary than last time. You could have phrased it x equals 2k for some k in the integers. I'm just trying to meet with as many people as possible, like communication wise. Pick something that feels right for you. I also use the word assume instead of suppose. Just a style difference, no particular reason other than exposing you guys. Okay, so we can write x as 2k, which means now we can plug something into our expression 3x squared plus x plus 14. So if we plug that in, we get this. And then we can simplify that a little bit. And then, let's give myself a little room. It's pretty easy to see you can factor out a 2 at this point. There we go. And then we can see that this is going to be an integer because all we're doing is multiplying and adding integers together. So then I can write this as 2k bar for some k bar equal to k squared plus k plus 7, which is in the integers. Please do not make me read this. Yeah, if you're running out of space like this, just flip to the next page. Okay. So there we go. We have written our expression as 2 times an integer. So now we can say there exists an integer such that our expression was equal to 2 times that integer. But we had x was even. That's important to note. So then we have x squared plus x plus 14 is even if x is even. That means we have integers that we haven't talked about yet. So next case, x is odd. So case 2, x is odd. So now we assume that x is going to be odd, which means we can write him as x equals 2k plus 1 for some k. Actually, no. Sorry, I'm just like trying to make you comfortable with all kinds of ways of writing this. But within a proof, you should try and be consistent. Why? It's good practice. So there exists k in z such that, there. Being consistent with my notation throughout my proof. I am not going to like yell at you guys that hard if you guys do little differences. So let's plug it in. I'm going, no, I'll write out some steps. I wanted to be lazy, but I can't really bring myself to be lazy. Okay, I will skip one step and I will just write the simplified version. There we go. And then we can clearly factor out a 2 from this. Which is equal to 2k bar for k bar equals 6x squared plus 7k plus 9, which is an integer. So then we have found the k bar or integer so that we can write this is equal to k times an integer. So then our expression is even when x is odd. And then we bring it all together. So when you're talking about integers, you either have even integers or you have odd integers. Therefore, we've taken care of all the possible integers. So since 3x squared plus x plus 14 is even when x is both even and odd, we know it's even for all the x's that are integers. Let's kind of get that done. Okay. QED, we are done. Box. All right. So that was an example of cases. I have one more example for cases where it's maybe a little bit less intuitive, and that's going to require introducing a little bit more terminology, a little bit more number theory, borrowing for right now. But it's, again, hopefully things that you already know, just written very formally. We've got a and b are integers, we can write a is equal to b times q plus r, where r is going to be less than b because that's the remainder. For instance, let me just illustrate with an example. So 2 did not divide 9, but you would maybe say, oh, it goes in 4 times, blah, 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 remainder of 1. So then what you could say is 9 is equal to 2 times q plus r, where q is equal to 4 and r is equal to 1. And you know, we've been practicing division for years at this point. We know the remainder has to be less than what we divided by right here. Otherwise, we did our division wrong. And that's why I've got r is less than b. Okay. I think I flipped the rules of a and b between my two definitions, and I apologize. If it makes you feel better, you can write it this way, because it's just writing things. It's just variables. There we go. Just a quick note. If r is equal to 0, then we could say that a divides b. All right, let's go ahead and do it for example b. So 38 would be equal to 7 times, 6 plus 2. So 6 would be q, and r would be 2. Okay. So with this in mind, we're going to prove something. So we want to prove that this expression is not divisible by 3. Let's try and think about things that we had already. So like I said, we could do like the whole even and odd thing. But like if you did plug in even stuff, so if we did case 1, n is even, n equals 2k, then we would get 8k squared plus 2k plus 1. And then how can I come up with some conclusion about dividing by 3? It's not helpful. What would be helpful is thinking about things involving 3. So we can think about n being a multiple of 3. You're like, but Gracie, we can't guarantee that it's a multiple of 3. That's restricting it. N is an integer. Not all integers are divisible by 3. Okay, very true. But we just got the division algorithm. So let's think about that. So we're going to say there exists assume. So assume n is an integer. Then we can use the division algorithm. Then there exists q and r such that n is equal to 3q plus r, where r is going to be equal to 0, 1, or 2. I am going to admit something. I dropped the unique quantifier. It doesn't matter. The important part is I can write it this way, and so I don't necessarily need to write that exclamation point. I just need them to be existent. Oops. Then I don't want to write things without saying where I got it from, by the division algorithm. Okay. So notice I didn't just go in guns blazing with my cases. I'm doing some prep work this time. So, what are my cases? Well, I could have n is divisible by 3, but I could have that when we divide by 3, it has a remainder of 1, or it could have a remainder of 2. Those are all things that I can say relating n to 3. So let's go in with cases. Case 1. N is divisible by 3. Then I can write n equals 3 times q. Or, can move that. If r equals 0, then I can write n equals 3q for some integer q. Cool. Let's plug it in. 2n squared plus n plus 1 is then going to turn into 18q squared plus 3q plus 1, which is equal to, we can factor out a 3 right here, but we still have this 1 left over. That's good. We wanted to prove it's not divisible by 3, so we want a remainder. This right here is an integer. Q is an integer. Q squared is an integer. 9 times q squared is an integer. That's an integer right there. So we have 3 times an integer plus something that falls into the remainder category. So I could say, so if we divide 2n squared plus n plus 1 by 3, we get a remainder of 1. Therefore, 3 does not divide 2n squared plus n plus 1. Okay, so that's one case. Now we have to do another case. Let's do the case when r is 1. So if r is 1, then we can say that, what is it? N is equal to 2q plus 1. So then we can plug that in. So 2n squared plus n plus 1 is equal to 18q squared plus 15q plus 4. And then I can factor a 3. It may be advantageous to think of this 4 as a 3 plus 1, because then it's going to factor like this. There we go. Okay. This is again an integer. That means if we were to divide this number by 3, we would still get a remainder of 1. And that's the case for n being divided by 3, having a remainder of 1. So if we divide n squared by have a remainder of 1. Therefore, 3 does not divide 2n squared plus n plus 1. Oops. Okay. Do I have to write that sentence about, so if we divide by 3, we have a remainder, blah, blah, blah? Yes. Yes, you do. Thank you for wondering. And thank you in advance for writing things out thoroughly. This is the class where we take time to write things very explicitly. So case 3, r is equal to 2. If r equals 2, then 3q, then n equals 3q plus 2. So then when we sub it in, we get 18q squared plus 27q plus 11. And we can write that as 3 times 6q squared plus 9q plus 3 plus 2. Again, this is an integer. So when we do our division, I'm making room for myself. So if we divide 2n squared plus n plus 1 by 3, we have a remainder of 2. Therefore, 3 does not divide 2n squared plus n plus 1. So there we go. We've exhausted every possible case. Like when it comes to dividing by 3, you can have a remainder of 0, 1, or 2. And then if you were to have a remainder of 3, that means it was divisible because you divided wrong. So those are the only possible things that can happen for n when we try to divide n by 3. So 2n squared plus n plus 1 cannot be divided by 3 for all n in the integers. You're like, did we really talk about all n in the integers? Yes, we did, because all integers, when divided by 3, have 3 choices for the remainder, and we went through all 3 choices. Done. Okay, so there you have it. We have our assumption. We can use our little arrow guy to get to our conclusion by bringing in definitions and theorems as needed. And sometimes we might need to break a proof into cases in order to exhaust all of our possibilities, but that's totally okay. And hopefully direct proofs weren't so bad. But that's all I have for you guys this time. See you next time.